What if one of history's most celebrated discoveries was not actually a discovery at all? That question might sound unusual at first. It might even seem disrespectful toward someone whose name has been attached to one of the most important ideas in the history of mathematics. But it is a question that serious researchers, historians, and mathematicians have been asking for a long time. And the more carefully they look at the evidence, the more difficult it becomes to give a clean answer. Most people encounter Pythagoras early in their education. The name appears in textbooks, in classrooms, in science documentaries, and in conversations about ancient knowledge. The theorem attributed to him is simple enough to explain to a child, yet powerful enough to support modern engineering, architecture, and physics. It states that in a right-angled triangle, the square of the longest side, the hypotenuse, is equal to the sum of the squares of the other two sides. It is elegant, it is precise, and it has carried the name of one Greek thinker for over 2,000 years. But this is where it becomes unclear, because the more historians dig into the ancient record, the more they find traces of this same idea appearing in places and times that do not fit the standard story. Not vague traces, not rough approximations, but precise, intentional, and repeated use of this exact mathematical relationship in civilizations that had no documented contact with ancient Greece, and in some cases existed centuries before Pythagoras himself was born. That is a fact that does not fit neatly into the explanation most people have been given. To understand why this matters, it helps to think about what it means to credit a discovery to a specific person. When we say that Pythagoras discovered the theorem, we imply something particular. We imply that before him, this knowledge did not exist in a meaningful form, that he or his followers were the ones who worked it out, demonstrated it, and contributed it to human understanding. That is a significant claim, and like all significant claims, it deserves scrutiny, especially when other evidence begins to appear. The evidence, as it turns out, is both older and more widespread than most people realize. Researchers studying the ancient world have found records from Babylonia, from India, from China, and from Egypt, all of which suggest that something very similar to the Pythagorean theorem was known and used long before the classical Greek world came into prominence. In some cases, the knowledge appears to predate Pythagoras by hundreds of years. In others, the gap stretches to more than 1,000, and yet the standard account of history continues to place his name at the center of the story. This raises questions that are not easy to dismiss. Some historians approach this by drawing a distinction between knowing a rule and proving it. They argue that earlier civilizations may have observed the relationship, that certain triangle measurements always behaved in a consistent way, without ever producing a formal mathematical proof of why that relationship holds universally. Under this view, what Pythagoras contributed was not the observation itself, but the logical demonstration that made it a proven theorem rather than a practical pattern. That is not an unreasonable position, but it depends on assumptions that are themselves difficult to verify, because in many cases, the written records from these earlier civilizations are incomplete, partially translated, or still being studied. Saying with certainty what they did or did not prove is harder than it might appear. And then there is another layer to this problem. Pythagoras himself left no writings. Not a single document survives that was written by the man himself. Everything known about him, his life, his travels, his ideas, his school, comes from accounts written by others, many of them composed hundreds of years after his death. Some of these accounts disagree with each other. Some contain legendary elements that historians treat with caution. The picture of Pythagoras that has come down through history is not a clear photograph. It is more like a reconstruction built from fragments, assumptions, and the perspectives of writers who had their own reasons for presenting him in a particular way. This does not mean the account is entirely wrong, but it does mean that treating it as firmly established fact requires more confidence than the evidence strictly supports. What makes this situation particularly interesting is that some ancient Greek writers themselves acknowledged that Pythagoras had traveled widely before establishing his famous school in southern Italy. He is said to have spent time in Egypt. He may have visited Babylon. Some accounts suggest contact with Persian scholars or other intellectual traditions of the ancient Near East. If those travels happened, and many historians believe they did, then the question naturally arises, What did he learn during those journeys? And is it possible that some of what he brought back to Greece was knowledge that already existed in the places he visited? This is not a fringe idea. It is a question that sits within mainstream historical scholarship, even if it is not always foreground in popular accounts. Historians of ancient mathematics have long recognized that the ancient world was more connected than later interpretations sometimes suggest. Trade routes carried not just goods but ideas. Scholars moved between civilizations. Intellectual knowledge was not always the exclusive property of the culture where it first appeared. The notion that one Greek thinker independently invented a theorem that cultures across Asia and North Africa had already been working with, without any acknowledgement of that prior knowledge, is something that deserves careful examination. At first, it seems reasonable to give Pythagoras the credit he has traditionally received. After all, the formal mathematical tradition that developed in ancient Greece was genuinely significant. Greek thinkers contributed enormously to the development of deductive reasoning, logical proof, and the kind of systematic mathematical thinking that later became the foundation of Western science. Those contributions are real, but this is where the explanation becomes difficult. Recognizing Greek achievement does not require erasing the achievement of others, and the more the historical record is examined, the clearer it becomes that others had been working with these same ideas for a very long time. Consider what it would actually mean for a civilization to use the right triangle relationship deliberately and precisely. It would mean that their engineers, builders, and mathematicians had a reliable method for constructing perfect right angles. It would mean they could calculate distances and areas with accuracy. It would mean they understood, at some level, a deep and non-obvious property of geometric space. These are not primitive or accidental capabilities. They require sustained intellectual effort, careful observation, and the kind of mathematical culture that takes generations to develop. When researchers find evidence of this capability in Babylonian clay tablets, in Indian religious texts, in Chinese mathematical manuals, the evidence points to something significant, something that does not dissolve easily into the story of one Greek philosopher on one Mediterranean island. But here is where the questions become more layered. Even if we accept that multiple civilizations independently develop knowledge of this relationship, that explanation carries its own complications. How often does the same non-obvious mathematical principle get discovered completely independently, in different parts of the world, across vastly different cultures? Some researchers find the idea of repeated independent discovery plausible. Others find it more difficult to accept. They argue that the level of sophistication involved, the specific numbers used, the particular ways the theorem was applied, suggests something more than coincidence. But drawing the line between parallel development and transmitted knowledge is something historians struggle with, because the evidence rarely tells the full story. What the evidence does tell us is this: the relationship between a right triangle sides was known, used, and in some cases explicitly described by multiple ancient civilizations before the name Pythagoras became attached to it. That is not a controversial statement among specialists. What remains less clear is exactly how that knowledge moved, how it was understood in each culture, and what role, if any, the tradition associated with Pythagoras played in connecting or formalizing ideas that were already circulating in the ancient world. And this uncertainty itself is worth sitting with. The history of mathematics is often presented as a clear line of progress, with specific individuals at specific moments making specific contributions. That is a useful simplification for teaching purposes. But simplifications have a way of obscuring what is actually more complicated. The origins of the Pythagorean theorem appear to be considerably more complicated than the name attached to it suggests. The theorem did not appear from nowhere in 6th century Greece. It emerged from a long and distributed history of mathematical thinking that stretched across multiple continents and several millennia. None of this means the standard account is entirely false. It means it is incomplete. It means there's more to the story, more civilizations involved, more centuries to account for, more unknowns in the historical record than most textbooks acknowledge. And the fact that this remains an area of active research and genuine scholarly debate tells us something important. The question has not been resolved. Researchers continue to study ancient tablets, to translate old manuscripts, to re-examine buildings and astronomical records in search of what earlier peoples understood and how they came to understand it. So when someone asks whether one of history's most celebrated mathematical discoveries was actually a discovery, at least in the way it is usually described, the honest answer is that we are not entirely sure. The name is settled. The history behind the name is not. And as the evidence continues to be examined, the picture that emerges is one of a world far more mathematically sophisticated, far more interconnected, and far more interesting than the simple story of one Greek genius with a theorem suggests. That is not a conclusion. It is a beginning, the beginning of a set of questions that, once you start asking them, are very difficult to stop. The official account of Pythagoras and his theorem is, on the surface, one of the cleaner stories in the history of human knowledge. A Greek thinker, a remarkable idea, a proof that changed mathematics. It is the kind of story that fits neatly into a textbook chapter, and that is exactly where most people first encounter it. The account has been repeated so many times, across so many centuries, in so many languages and educational systems, that it has taken on the quality of settled fact. But settled and proven are not always the same thing. And when this particular account is examined more carefully, certain details begin to look less stable than they first appear. Pythagoras of Samos is described, in most historical summaries, as a philosopher and mathematician who lived approximately between 570 and 495 BC. He was born on the Greek island of Samos, in the eastern Aegean Sea. At some point in his adult life, he left Samos and eventually settled in Croton, a Greek colony located in what is now southern Italy. There, he founded a community of followers, a school, or perhaps something closer to a religious brotherhood, that studied mathematics, music, philosophy, and what the members believed were the hidden numerical patterns underlying all of reality. This group is referred to by historians as the Pythagoreans, and it is from this group, according to tradition, that the famous theorem emerged. The theorem itself is stated clearly in most introductions. In any right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. It is one of those ideas that, once understood, seems almost obvious, almost inevitable, and yet it describes something genuinely profound about the geometry of flat space, a relationship that holds without exception for every right triangle that has ever existed or will ever exist. The claim that Pythagoras or his followers were the first to formally prove this relationship is the centerpiece of his historical reputation. It is why the theorem carries his name. But this is where the first complications appear. When historians look for direct evidence of Pythagoras's life and work, they run into a problem that is difficult to overstate. No writings by Pythagoras himself have survived. Not a fragment, not a single line that can be traced with confidence to his own hand. This is not entirely unusual for ancient thinkers. Many of them wrote little or nothing, and what they did write was lost over centuries of time. But in the case of Pythagoras, the absence of primary sources is particularly significant, because virtually everything claimed about him rests on accounts written by other people, often centuries after his death. The earliest substantial accounts date from several hundred years after he lived. This means that every detail of his biography, his birth, his travels, his ideas, his school, his personality, is filtered through writers who never met him, who were working from earlier sources that are themselves no longer available, and who had their own philosophical and cultural reasons for presenting him in particular ways. Some believe this is not a serious problem. Many ancient figures are known only through second-hand accounts, and historians have developed methods for evaluating the reliability of such sources. Others disagree. They point out that in the specific case of Pythagoras, the second-hand accounts are unusually varied and sometimes contradictory. Different ancient writers describe him differently. Some portray him as a rigorous mathematician. Others focus on his mystical beliefs about the soul and the afterlife. Some describe miracles attributed to him. The image shifts depending on which source is consulted, and when sources disagree to this degree, it becomes difficult to know which version, if any, accurately reflects the historical person. This raises a question that sounds simple, but is surprisingly difficult to answer. What do we actually know about Pythagoras that can be verified? At first, it seems reasonable to focus on what is widely agreed upon. He was from Samos. He founded a community in Croton. His followers developed significant mathematical and philosophical ideas. But even these basic points require some qualification. The founding of the school in Croton is well attested in multiple sources, which gives it reasonable credibility. But the internal workings of that school, the specific contributions of Pythagoras versus his followers, and the question of who exactly developed what, these are far murkier. The Pythagoreans reportedly had a tradition of attributing all discoveries made within the community to Pythagoras himself, as a kind of collective honorific. If that is true, then even within the ancient world, the attribution was less personal and more institutional than the name implies. The theorem may have emerged from a group effort that was later simplified into a single name. And this is where the explanation becomes more difficult, because even if we set aside the question of individual versus group discovery, there remains a deeper issue. The claim that the Pythagoreans were the first to formally prove the theorem cannot be verified from existing records. No document survives that contains the Pythagorean proof in its original form. Later Greek mathematicians, most notably Euclid, who compiled his famous Elements several centuries after Pythagoras, did present rigorous proofs of the theorem. But Euclid was not Pythagoras, and his work came significantly later. The connection between Pythagoras and a formal proof is asserted by ancient writers, but those assertions cannot be cross-checked against the original source, because the original source does not exist. This does not mean the assertion is false. It may well be that Pythagoras or his followers did produce a proof that has simply been lost to time, as so many ancient documents were. The absence of evidence is not the same as evidence of absence, but it does mean that one of the central claims in the official account, that Pythagoras gave the world a formal mathematical proof, rests on a chain of sources that cannot be fully verified. That is a meaningful distinction, particularly when the theorem's origins are being compared across cultures and time periods. Some scholars point out that ancient Greek writers themselves acknowledged Pythagoras's extensive travels before he founded a school. This detail appears in multiple ancient sources, and most historians treat it as credible. Pythagoras is said to have visited Egypt, where he may have studied with priests or learned from local mathematical traditions. He is reported to have traveled to Babylon, which at the time was one of the most intellectually advanced regions in the ancient world. Some accounts mention additional travels to Persia or other parts of the Near East. The specifics vary by source, and the duration and nature of these journeys are not clearly recorded. But the general picture of a young thinker moving through several of the major intellectual centers of the ancient world before returning to establish his own school is consistent enough across sources that it is taken seriously by most historians. But this is where it becomes unclear. If Pythagoras traveled to Egypt and Babylon before developing his mathematical ideas, then the question of intellectual influence becomes impossible to ignore. Egypt had been using geometric principles in construction for millennia. Babylon had a rich tradition of mathematical calculation that included, as will be examined more closely later, some remarkably sophisticated work with right triangle relationships. If a young Greek thinker spent years in those places, learning from priests, scribes, and scholars, is it not reasonable to ask whether the ideas he later became famous for were already present in the places he visited? This question makes some people uncomfortable, because it seems to diminish an important historical figure. But that is not necessarily the right way to look at it. Learning from others is not the same as stealing from them. Many of history's most significant intellectual contributions have involved taking existing ideas, synthesizing them, extending them, and presenting them in new forms. If Pythagoras encountered early forms of right triangle knowledge in Babylon or Egypt, and then worked with his followers to formalize and prove those relationships in a rigorous way, that could itself be a meaningful contribution, even if the underlying observation was not entirely new. The problem is that the official account does not really address this possibility. It presents Pythagoras as an originator, not a synthesizer, and that framing may be giving an incomplete picture. At first, it seems normal that a civilization as mathematically sophisticated as ancient Greece would develop its own geometric theorems. But there is a problem. Greece in the 6th century BCE was not working in isolation. It was embedded in a broader Mediterranean and Near Eastern world, with active trade, diplomatic contact, and intellectual exchange across many regions. Greek thinkers were known for their curiosity and their willingness to travel. Thales, who is often considered the first Greek philosopher and who was a contemporary of Pythagoras, is also said to have traveled to Egypt and to have brought back geometric knowledge. This pattern of Greek thinkers learning from older civilizations and then developing what they learned within their own intellectual tradition is not a secret. Historians acknowledge it, but it tends to get underemphasized when individual Greek figures are celebrated for their discoveries. And there is another dimension to this that does not fully make sense within the standard framing. The theorem that carries Pythagoras' name was not considered, even within the ancient Greek tradition, to be a simple or isolated observation. Euclid's proof of it in the Elements is one of the most elegant and involved proofs in the entire work. The theorem connects to deep ideas about proportion, area, and the structure of space. If something this significant was truly derived from scratch, without any prior tradition of knowledge about right triangle relationships, that would be extraordinary. It would represent a kind of mathematical leap that has almost no parallel in the history of science, where even the greatest discoveries almost always build on earlier work. So the question lingers, what prior work was Pythagoras building on, and where did that work come from? The explanation the textbooks offer is not wrong in every respect. Pythagoras was real. His school existed. Greek mathematics was enormously important. The theorem is correctly stated and universally valid. None of that is in dispute. But the story that places Pythagoras as the sole or primary origin point of this mathematical knowledge, the story that is repeated in classrooms and encyclopedias, that story rests on shakier foundations than it is usually given credit for. The sources are secondhand. The proof cannot be verified in its original form. The travels to Egypt and Babylon raise unresolved questions about influence and transmission. And as the evidence from other ancient civilizations begins to accumulate, those questions become harder and harder to set aside. The official explanation, in other words, is not a complete picture. It is a version of the history, an influential and long-standing version, but one that leaves out a great deal of what the broader record suggests. And as that broader record continues to be studied, the gaps in the standard account become more visible. The regions Pythagoras is said to have visited, Egypt, Babylon, and others, were not mathematically empty before he arrived. They had their own traditions, their own knowledge, their own ways of working with geometric relationships. What those civilizations knew, and how long they had known it, is a question that changes the shape of the entire story. Sometimes the most important challenge to an accepted idea does not come from a new theory or a bold argument. It comes from an object, a physical thing that has survived long enough for someone to look at it carefully and realize that it does not fit the story being told. In the case of the Pythagorean theorem, that object is a small clay tablet. It is not impressive to look at. It is broken at one corner, worn at the edges, and covered in markings that most people today cannot read without significant training. But what those markings say, and what they imply about when and where advanced mathematical knowledge first appeared, is one of the more quietly unsettling findings in the entire history of mathematics. The tablet is known by a catalog number, Plimpton 322. It takes its name from George Arthur Plimpton, an American publisher and collector of rare documents who acquired it sometime around 1922. At the time, it was purchased as an old business record, possibly a list of commercial transactions. Nobody was entirely sure what it was. For years it sat in a collection, studied occasionally, but not fully understood. Then, in 1945, historians of mathematics Otto Neugebauer and Abraham Sachs examined it in detail. What they found completely changed how scholars thought about ancient Babylonian mathematics, and it introduced a question that has not been fully resolved since. The tablet dates to approximately 1800 BC. That places it in the Old Babylonian period, a time when the civilization centered in Mesopotamia, in what is now Iraq, was one of the most sophisticated in the world. The Babylonians had developed writing, law, astronomy, agriculture, and trade on a remarkable scale. They also had mathematics, but until Plimpton 322 was properly analyzed, the full extent of their mathematical knowledge was not widely appreciated outside specialist circles. The 1945 analysis made it impossible to ignore, because what the tablet contains is not a simple list of numbers. It contains a systematic, organized table of what mathematicians call Pythagorean triples. To understand why this matters, it helps to be clear about what a Pythagorean triple is. It is a set of three whole numbers that satisfy the right triangle relationship exactly. The most familiar example is 3, 4, and 5. If you square 3, you get 9. If you square 4, you get 16. 9 plus 16 equals 25. And 25 is the square of 5. So 3, 4, 5 forms a perfect right triangle with no remainders, no approximations, and no rounding required. There are infinitely many such sets of numbers, but finding them is not trivial. The larger the numbers involved, the harder they are to identify through simple observation or trial and error. And yet Plimpton 322 does not just list one or two of these triples. It lists 15 of them, organized in columns, with a structure that suggests whoever created the tablet was not just recording examples, but working within a systematic mathematical framework for generating them. This is not a coincidence. That is the point that researchers keep returning to. These numbers do not appear by accident. They are not the kind of figures you stumble across while measuring land or cutting stone. To produce a table of 15 Pythagorean triples, including triples involving large numbers far beyond the simple 3, 4, 5 example, requires deliberate mathematical thinking. It requires someone who understands the underlying structure of the relationship, not just an isolated instance of it. And the tablet does not come from 6th century Greece. It does not come from the time of Pythagoras or his followers. It comes from Babylon, and it was created more than 1,000 years before Pythagoras was even born. Let that timeline settle for a moment. More than 1,000 years. If Pythagoras lived around 570 to 495 BCE, and this tablet dates to approximately 1800 BCE, the gap between them is not small. It is not a matter of decades or even a century or two. It is a stretch of time longer than the entire period from the fall of the Roman Empire to the present day. And within that vast stretch of time, before Greece had developed its famous philosophical and mathematical tradition, scribes in Babylon were already recording organized tables of right triangle number relationships on clay. This raises questions that the standard historical account does not address in a fully satisfying way. At first, it seems normal to respond to this by drawing a distinction between practical knowledge and theoretical proof. Some historians do exactly that. They argue that the Babylonians may have known about Pythagorean triples as numerical curiosities, useful for construction or land measurement, without ever developing a general proof that the relationship holds for all right triangles under all conditions. Under this view, what Pythagoras contributed was the abstract, universal proof. The Babylonians had examples. The Greeks had the theorem in its true mathematical sense. This is a reasonable distinction to make in principle. Proof matters in mathematics. A table of examples and a logical demonstration of universal truth are genuinely different things. But there is a problem, and it is a problem that the distinction does not fully resolve. The structure of Plimpton 322 suggests more than casual observation of a few convenient number patterns. The 15 triples listed on the tablet are not random. They are arranged in a specific order, and the numbers involved are not small or simple. Some of the triples on the tablet involve numbers in the hundreds, values that would be extremely difficult to discover through trial and error or through practical construction alone. Researchers who have studied the tablet in depth believe that whoever created it had a method for generating these triples, a systematic approach, which implies a level of mathematical understanding that goes beyond simply noticing that certain triangles behave consistently. And this is where it becomes unclear, because if the Babylonian scribes had a method for generating Pythagorean triples, if they understood the structure well enough to produce a systematic table, then the question of whether they had something approaching a proof becomes much harder to dismiss. A proof in the formal Greek sense is a specific kind of demonstration, built from axioms and logical steps. But understanding why a mathematical relationship works, and being able to use that understanding to generate new examples systematically, is not entirely different in nature. It does not fit neatly into the category of pure ignorance. The Babylonians may not have written their understanding in the form of a formal deductive proof, but that does not mean their understanding was shallow. There is another layer to this that deserves attention. The Babylonian number system was different from the one we use today. They worked in base 60, rather than base 10. This is actually a highly practical system for mathematics involving fractions and divisions, because 60 is divisible by many more numbers than 10. Their scribes were trained to work with complex calculations, and their mathematical tablets show a level of computational skill that surprised many modern historians when those tablets were first translated and studied. The people who created Plimpton 322 were working within a sophisticated mathematical culture. They were not beginners stumbling across patterns by accident. They were trained professionals operating within an established tradition of numerical and geometric reasoning. This does not mean the Babylonians had everything that later mathematicians would develop. It does not mean their knowledge was complete or that they had answers to every question the Greeks eventually asked. But it does mean that framing them as people who merely noticed a useful coincidence, while reserving the real mathematical achievement for Greece, may not be fully accurate. And this is where the explanation becomes difficult, because the closer researchers look at what the Babylonians actually recorded, the harder it becomes to maintain a clean separation between their knowledge and what is usually described as the Greek contribution. The discovery of Plimpton 322 did not settle the debate. It opened it. After Neugebauer and Sachs published their analysis, other scholars began examining Babylonian mathematical tablets more carefully. What emerged was a broader picture of Babylonian mathematics that had previously been underappreciated. Other tablets showed that Babylonian scribes could calculate square roots with considerable precision. They worked with quadratic equations. They solved problems involving areas and volumes that would require significant algebraic thinking to approach formally. The mathematics of ancient Babylon was not primitive. It was, in certain respects, ahead of where many historians had assumed it to be. Some researchers, after absorbing all of this evidence, have argued that the question of who deserves credit for the Pythagorean theorem needs to be fundamentally reconsidered. They suggest that the theorem's name reflects a historical accident, the fact that Greek texts were preserved and transmitted into the Western tradition more effectively than Babylonian clay tablets, which sat buried and unread for thousands of years. Under this view, Pythagoras became the name attached to the theorem not because Greece was first, but because Greece's records were more accessible to later European scholars. It doesn't fully make sense to credit the naming with the discovering, but that is, more or less, what has happened. Others push back. They argue that the Greek contribution was genuinely distinct, and that formal proof, the logical demonstration that a relationship holds universally, is not just a procedural nicety, but a fundamental step in the development of mathematics as a discipline. Without proof, mathematics risks becoming a collection of useful observations that happen to work in practice, without anyone fully understanding why. The Greek tradition of deductive proof, they argue, was transformative in a way that Babylonian numerical sophistication, impressive as it was not. Some believe this distinction is enough to justify the way history has assigned credit. Others disagree and find the distinction less convincing when applied to Plimpton 322 specifically. What is not disputed is the tablet itself. It exists. It has been dated. The numbers it contains have been analyzed by multiple researchers over several decades. And the conclusion, that Babylonian scribes were working with Pythagorean triples in an organized and systematic way more than 1,000 years before Pythagoras, is not a fringe claim. It is the consensus position among historians of ancient mathematics. The debate is not about whether the tablet shows this knowledge. It does. The debate is about what that knowledge means, how deep it went, and what conclusions should be drawn from it about the history of the theorem and the civilization credited with its discovery. And that debate, as it turns out, is only the beginning, because Babylon is not the only place where researchers have found evidence that this knowledge existed long before Greece. Other civilizations, in other parts of the ancient world, left their own records, and some of those records raise questions that are, in some ways, even harder to explain than a clay tablet from Mesopotamia. The picture of ancient mathematical knowledge that is slowly emerging from these findings is more complex, more global, and more surprising than the standard account has ever suggested. What Plimpton 322 established is a starting point, a crack in the official explanation, and once that crack appears, it is very difficult to look at the history of mathematics the same way again. Babylon presents one kind of challenge to the standard account. The clay tablet, the organized numbers, the systematic table of right triangle relationships recorded more than 1,000 years before Pythagoras. That challenge is concrete and specific. It points to a particular object, a particular civilization, and a particular moment in time. But Babylon is not the only case that demands attention. To understand how widespread this mathematical knowledge may have been across the ancient world, it helps to look at a completely different civilization in a completely different part of that world. And Egypt, which sits geographically between Mesopotamia and the Mediterranean, presents a case that is interesting in its own right, and in some ways more complicated to evaluate. Egypt is one of the most studied ancient civilizations in history. Its monuments have attracted researchers, travelers, and scholars for centuries. Its written records have been analyzed in remarkable depth since the decipherment of hieroglyphics in the 19th century. And yet, despite all of that study, certain questions about how Egypt's builders and surveyors actually worked remain genuinely unresolved. The mathematical knowledge that must have underlain some of Egypt's most famous achievements is not always clearly documented in the records that survive. And this gap between what the physical evidence implies and what the written record confirms is itself a significant part of the problem. To understand the Egyptian case, it helps to start with geography and agriculture. Ancient Egypt was entirely dependent on the Nile. The river's annual flooding was the foundation of the civilization's food supply. When the Nile flooded each year, it deposited rich silt across the agricultural land on either bank, renewing the soil's fertility and making large-scale farming possible in an otherwise arid landscape. But that flooding also erased something important. It wiped away the boundary markers that defined individual plots of land. When the waters receded, farmers and officials needed to re-establish those boundaries precisely. Getting them wrong would mean disputes, unfair taxation, and social conflict. So accurate land measurement was not a luxury in ancient Egypt. It was a practical necessity that the state took seriously. This is where a particular group of workers enters the picture. Ancient Egyptian texts refer to surveyors whose job involved measuring and re-establishing land boundaries after the flood. These individuals used ropes as their primary measuring tool, and because of this, they have come to be described in historical literature, and in some ancient sources, as rope stretchers. The image is straightforward. Workers carrying long, carefully knotted ropes, laying them out across the land to measure distances and establish correct angles for fields and structures. The rope was their instrument, and according to a description that appears frequently in accounts of Egyptian surveying, those ropes could be arranged in a very specific way to create a perfect right angle. The method, as it is commonly described, involves a rope divided into 12 equal segments by knots. When this rope is arranged into a triangle with sides of 3 segments, 4 segments, and 5 segments, the angle between the 3 side and the 4 side is exactly 90 degrees. This works because 3, 4, and 5 form a Pythagorean triple. They satisfy the right triangle relationship precisely. The corner of the triangle that sits between the shortest and middle sides is always a perfect right angle. If Egyptian surveyors used this method, they were effectively applying the Pythagorean relationship in practical work, regardless of whether they understood the underlying mathematics in a formal sense. But this is where it becomes unclear, because the evidence for this specific rope-stretching method in ancient Egypt is not as straightforward as popular accounts often suggest. The idea has been widely repeated in books, documentaries, and educational materials, as though it were an established historical fact, and in some ways it has taken on the quality of received wisdom. But when researchers look carefully at the primary sources, they find that the direct documentary evidence for the 12-segment rope and the 3-4-5 triangle specifically is limited. Egyptian texts do describe rope stretchers as surveyors. They do confirm that ropes were used as measuring tools. What they do not always provide is a clear and explicit description of the 3-4-5 triangle method being used systematically. Some scholars argue that this specific technique has been inferred more than it has been proven, and that the inference, while plausible, should not be presented as certain. This does not mean the practice did not exist. An absence of documentation is not the same as evidence that something did not happen. Many practical techniques in the ancient world were passed down through training and demonstration rather than written instruction. A rope stretching method that worked reliably would not necessarily be written down in a formal text. any more than a modern craftsperson would write detailed instructions for a technique they learned by watching someone else. The method may have been widely used and simply not recorded in the documents that have survived. But that uncertainty is itself significant. It means that the Egyptian case, unlike the Babylonian tablet, cannot be pointed to as definitive documented evidence of the right triangle relationship being applied deliberately and systematically. And yet the physical evidence that does survive, the pyramids and other large-scale construction projects, raises a related question that is difficult to set aside. The Great Pyramid of Giza, built around 2560 BCE, is a structure of extraordinary geometric precision. Its base is nearly a perfect square, with sides differing from each other by less than a fraction of a percent. Its corners are very close to perfect right angles. Its faces rise at consistent angles. The internal chambers and passages are built with a level of accuracy that required careful planning and measurement. The structure is not an approximation. It is a demonstration of geometric control at a scale and precision that is genuinely remarkable given the tools and methods available at the time. The question this raises is simple, but not easy to answer. How did the builders of the Great Pyramid achieve that level of geometric precision without a deep understanding of the mathematical relationships involved? At first, it seems possible that the precision could be explained by careful practical measurement, by trial and error, by checking and correcting, by accumulated craft knowledge that did not require formal mathematical understanding. Some researchers take this position. They argue that skilled workers with good tools and careful methods can achieve high precision without needing to understand the abstract principles behind what they are doing. But there is a problem with this explanation when it is applied to structures of this scale and complexity. The Great Pyramid is not a small building where small errors can be corrected as you go. It is a structure that required planning before construction began, decisions about angles, proportions, and alignment that had to be worked out in advance. If those decisions were wrong, the consequences would compound as the structure rose. Fixing a significant geometric error partway through building a pyramid would be, in practical terms, nearly impossible. So the precision that exists in the final structure implies that the planning that preceded it was accurate. And accurate planning at that level implies a mathematical framework that could produce reliable results before construction started. This does not prove that Egyptian builders used the Pythagorean relationship. It does not prove they had formal geometric knowledge in any specific sense, but it makes the question harder to dismiss. The gap between what the physical evidence implies and what the written record confirms is real, and it is wide. And sitting inside that gap is a question that researchers have approached from many directions without reaching a fully satisfying answer. What mathematical knowledge did the builders of the pyramids actually have, and how did they apply it? Some Egyptologists point to a document called the Rhind Mathematical Papyrus, which dates to around 1550 BCE and contains a collection of mathematical problems and solutions. It shows that Egyptian scribes could calculate areas, volumes, and proportions with considerable skill. It demonstrates familiarity with fractions, with basic algebra in a practical sense, and with geometric relationships relevant to construction. But it does not contain an explicit statement of the Pythagorean theorem in the way that the Sulba Sutras from India do, or the way that Babylonian tablets demonstrate through their organized tables. The papyrus shows mathematical competence. It does not clearly show the same depth of right triangle knowledge that Plimpton 322 implies for Babylon. And this is where the explanation becomes difficult. Because Egypt sits at the crossroads of the ancient world, it had contact with Babylon, with the Near East, with the Mediterranean civilizations that would eventually include Greece. If right triangle knowledge was circulating in Babylon as early as 1800 BCE, and the evidence strongly suggests it was, then Egypt, which was in regular contact with Mesopotamian civilization, might well have had access to similar knowledge. The possibility of transmission is real. But transmission and independent development are two very different things, and distinguishing between them, in the absence of clear documentary evidence, is something historians find genuinely difficult. What the Egyptian case adds to the broader picture is a kind of uncertainty that is itself informative. Here is a civilization capable of extraordinary geometric precision in construction. Here are workers who used ropes as measuring tools and who needed to establish right angles accurately for both agricultural and architectural purposes. Here is a mathematical tradition sophisticated enough to produce the Rhine papyrus, and yet the direct documentary connection between all of that and a specific understanding of the right triangle relationship remains elusive. The physical evidence points in one direction. The written record is less clear, and the space between those two things is filled with questions that have not been resolved. That ambiguity matters because it reflects a broader challenge in understanding ancient mathematical knowledge. The absence of a written proof does not mean the knowledge was absent. Practical application without formal documentation is not the same as ignorance. A civilization that built structures of extraordinary geometric precision, whose surveyors used rope-based measurement methods, and whose scribes produced sophisticated mathematical papyri, that civilization deserves to be taken seriously as a potential site of right triangle knowledge, even if the evidence is not as clean or direct as a clay tablet with 15 organized rows of Pythagorean triples. Egypt, in other words, adds a dimension to the story that does not simplify it. It raises the possibility of widespread geometric knowledge across the ancient world without providing the kind of definitive evidence that settles the question. And as more civilizations enter the picture, each with their own records, their own construction achievements, their own mathematical traditions, the story becomes correspondingly more layered. The rope stretchers of ancient Egypt may or may not have understood exactly what they were doing in mathematical terms, but that uncertainty is part of what makes the broader question so difficult to resolve. And difficult questions, when they keep resisting resolution, are often pointing towards something important that has not yet been fully understood. Every piece of evidence examined so far has come with its own complications. The Babylonian tablet is concrete and specific, but the question of what it proves about the depth of Babylonian understanding remains open. The Egyptian case is suggestive, even compelling when the physical structures are considered, but the documentary evidence is thinner than popular accounts sometimes imply. Each civilization adds something to the picture. Each one also leaves something unresolved. And then, moving further east across the ancient world, another piece of evidence appears. This one is different in character from what has come before. It is not a clay tablet filled with numbers. It is not a stone pyramid whose precision implies geometric knowledge. It is a body of text, written language that describes geometric relationships directly, explicitly, and in a way that leaves considerably less room for interpretation than either of the previous cases. The texts in question are known as the Sulba Sutras. The name itself offers a clue to their nature. In Sanskrit, the word sulba refers to a cord or rope used for measurement, and sutra means a rule or thread of teaching. So the Sulba Sutras are, in a literal sense, rules of the measuring cord. They are a collection of ancient Indian texts that deal specifically with the geometry required to construct altars used in Vedic religious rituals. These are not general mathematical treatises in the modern sense. They were written for a very practical and specific purpose, to give precise instructions for building sacrificial altars of particular shapes and areas, because the shape of an altar was considered spiritually significant in the Vedic tradition. Getting the geometry wrong was not merely an aesthetic failure, it was a religious one, and that meant the geometric instructions in these texts had to be accurate. To appreciate what makes the Sulba Sutras significant in the context of this investigation, it helps to understand what kind of geometry they contain. Building altars of specific shapes and areas, particularly when those shapes had to be transformed from one form to another while keeping the area exactly the same, required genuine geometric knowledge. For example, a ritual might demand an altar in the shape of a square, and then a separate ritual might demand an altar of exactly the same area, but in the shape of a circle, or a falcon, or a different geometric figure. Solving problems like these requires understanding geometric relationships at a level that goes beyond simple measurement. And within those solutions, the Sulba Sutras contain clear statements of the right triangle relationship, the relationship that the Western tradition has come to call the Pythagorean theorem. The statement is not buried or implied. It is articulated directly. One of the most frequently cited passages from the Sulba Sutra states, in a form that translates roughly as, the diagonal of a rectangle produces both areas, which its length and breadth produce separately. This is a description of the Pythagorean relationship expressed in geometric rather than numerical terms. It says that the square built on the diagonal of a rectangle equals the sum of the squares built on the two sides. That is the theorem, stated clearly, applied to real construction problems, written in a language and tradition completely separate from ancient Greece. Now, the dating of these texts is where the first serious complication enters. Scholars do not agree on when the Sulba Sutras were composed. Estimates vary, and the range of those estimates is wide enough to matter significantly for how the evidence is interpreted. Some researchers place the earliest of the Sulba Sutras, particularly texts attributed to authors named Bodhayana and Apastamba, somewhere in the range of 800 to 600 BCE. Others argue for dates closer to 500 BCE. And some researchers suggest that the written texts represent the recording of knowledge that had existed in oral form for considerably longer, rooted in a tradition of mathematical and ritual knowledge that predates the written versions by an uncertain but potentially significant period of time. Each of these dating estimates leads to a different conclusion about the relationship between Indian and Greek mathematical knowledge. If the more conservative estimates are accepted, if the earliest Sulba Sutras date to around 500 BCE, then they overlap with the period when Pythagoras is believed to have been active. They do not clearly predate him. They sit beside him in time, in a completely different part of the world, containing the same fundamental geometric insight. That alone is striking. But if the earlier estimates are accepted, if these texts or the knowledge they record go back to 800 BCE or further, then India, like Babylon, possessed this knowledge centuries before Pythagoras was born. And if the oral tradition argument has merit, if mathematically trained priests and builders were working with these geometric relationships long before anyone wrote them down, then the timeline extends even further into the past, in a direction that is difficult to map precisely. This is where the comparison with the Babylonian case becomes important. Plimpton 322 shows numerical knowledge, a table of right triangle number relationships organized in columns. What it does not contain is a verbal or geometric statement of the underlying rule. The tablet shows that Babylonian scribes could identify and organize Pythagorean triples. It implies mathematical understanding, but it does not explicitly state the theorem as a general geometric principle. The Sulba Sutras do something different. They articulate the relationship in a way that is closer to what mathematicians would recognize as a general statement, a rule that applies not just to specific numbers, but to geometric figures in general. This distinction matters. It moves the Indian evidence into a different category from the Babylonian evidence, and that shift is significant when evaluating the broader history of this mathematical idea. But this is where it becomes unclear, because recognizing the significance of the Sulba Sutras immediately raises a different set of questions. The most pressing one is about independence. Did the mathematical tradition that produced these texts develop its understanding of the right triangle relationship entirely on its own, without any contact with or influence from Babylon or other ancient mathematical cultures? Or was there some channel of transmission, some path through which geometric knowledge moved from one civilization to another across the ancient world? These are not simple questions, and the honest answer is that historians do not have a clean resolution to offer. The ancient world was not as isolated as it is sometimes imagined. Trade routes connected South Asia to Persia, Persia to Mesopotamia, and Mesopotamia to Egypt and the Mediterranean. Merchants, diplomats, and traveling scholars moved along these routes. Ideas and knowledge traveled with them. It is not difficult to construct a theoretical pathway through which mathematical knowledge could have moved between Babylon and the Indian subcontinent, or between Egypt and Persia and India. The geography allows for it. The historical record of contact between these regions, while incomplete, does not suggest the kind of total isolation that would make independent development the only possibility. At first, it seems straightforward to ask which direction the knowledge flowed, if it did flow. Did Babylonian mathematical knowledge travel east and influence the Vedic tradition? Did Indian geometric knowledge travel west and reach Babylon or Egypt? Or did parallel developments occur in multiple places, each driven by the same practical needs, construction, land measurement, ritual architecture, that would naturally lead mathematically inclined thinkers toward the same fundamental geometric relationship? None of these possibilities can be ruled out, and none of them can be confirmed with the evidence currently available. This is not a comfortable position for anyone who wants a clean historical narrative, but it is the honest position. Some researchers who specialize in the history of ancient Indian mathematics argue strongly for independent development. They point to the specific character of the Sulba Sutras, the way they are embedded in a distinctly Vedic religious and intellectual context, the particular problems they are solving, the vocabulary and framework they use, as evidence that this is a homegrown tradition. Under this view, the right triangle relationship was discovered independently in India because the practical problems of altar construction made it necessary, and because the mathematical culture of the Vedic tradition was sophisticated enough to identify and articulate the underlying principle. This is a coherent argument, and there is no direct evidence that contradicts it. Others are less certain. They note that the timing of the Sulba Sutras, even on the earlier estimates, comes after the period when Babylonian mathematical knowledge was clearly well established. They point to the general pattern of knowledge exchange across the ancient world and suggest that the absence of a documented transmission pathway does not mean transmission did not occur. Under this view, the similarity between Babylonian numerical knowledge of Pythagorean triples and the geometric statements in the Sulba Sutras is too close to be confidently attributed to coincidence. But this argument also cannot be proven from existing records. The debate remains genuinely open, and this is where the explanation becomes difficult, because what the Indian evidence introduces, that neither Babylon nor Egypt quite managed on its own, is the combination of two things at once. First, a clear verbal statement of the geometric principle, not just numbers, not just physical structures, but an articulated rule. And second, a temporal position that either overlaps with or predates Pythagoras, depending on which scholarly estimates are accepted. Together, these two features place the Sulba Sutras in a particularly interesting position within the broader argument about where this mathematical knowledge originated and how it traveled. The inconsistency that this creates within the standard historical account is real and not easily dismissed. If one civilization, Babylon, had knowledge of Pythagorean triples more than 1,000 years before Greece, that is already a significant challenge to the conventional story. But if a second civilization, India, articulated the theorem as a general geometric principle at roughly the same time as Pythagoras, or possibly earlier, and did so in a completely separate intellectual tradition, then the challenge becomes harder to contain. Two data points suggest a pattern, and patterns, in historical investigation, demand explanation. It doesn't fully make sense to maintain that Pythagoras introduced this idea to the world when the world, apparently, already had the idea in more than one place. Some believe the Greek contribution was the formal deductive proof, the logical demonstration that the relationship is universally true. Others point out that the Sulba Sutras contain methods that approach proof in some respects, even if they do not match the formal Greek style. The line between stating a rule clearly and proving it rigorously is real, but it is also a line that can be drawn in more than one place, depending on what is meant by proof, and where exactly that line falls, in relation to the Indian texts, is something that scholars continue to debate without reaching full agreement. What the Sulba Sutras make clear, above all else, is that the right triangle relationship was not a secret held only by ancient Greece or discovered only in the Mediterranean world. It was part of a mathematical tradition on the Indian subcontinent that was sophisticated, deliberate, and concerned with precision. Whether that tradition developed independently, received knowledge from elsewhere, or contributed knowledge to other civilizations is a question that remains open. But the texts themselves are not ambiguous. The geometric knowledge is there, clearly stated, applied to real problems, and located in a time and place that does not fit the standard account of how and where this mathematical idea first emerged. Each civilization examined so far has added something new to the picture. Babylon contributed a clay tablet with organized numerical knowledge dating back more than 1,000 years before Pythagoras. Egypt raised questions through the precision of its construction and the practices of its surveyors, even if the documentary evidence remained thinner than the physical evidence implied. India produced written texts that articulated the right triangle relationship as a general geometric principle, in a tradition that either overlapped with or predated the Greek mathematical tradition, depending on which scholarly estimates are accepted. Each case was located in a region that had some degree of connection, however indirect or poorly documented, to the broader ancient world that eventually produced Greece. Trade routes existed. Contact between civilizations was possible. The question of transmission, while unresolved, could at least be raised without straining credibility. But then the geographic scope of the evidence expands further. And when it does, the explanations that have been available up to this point begin to feel less adequate. Because the next civilization to enter this investigation is not located in the Near East or South Asia. It is not connected to the Mediterranean world by well-documented trade networks. It is not a civilization whose contact with Babylon or Egypt can be traced through surviving records. The next piece of evidence comes from ancient China, and that shift in geography changes the nature of the problem in a way that is difficult to account for within the frameworks that have been applied so far. China in the ancient period was, by most measures, a world unto itself. Its civilization developed largely independently of the civilizations further west. Its writing system was distinct. Its political structures, religious traditions, and intellectual culture followed paths that were shaped by local conditions and local history rather than by extensive contact with Babylon, Egypt, or Greece. The Silk Road, which would eventually connect China to the Mediterranean world, did not become an active corridor of exchange until around the 2nd century BCE. And even then, the transmission of ideas along that route was slow, incomplete, and unevenly documented. Before that period, the intellectual distance between China and the civilizations of the ancient Near East and Mediterranean was vast. And this is precisely what makes the Chinese mathematical evidence so difficult to explain away. The text at the center of this discussion is called the Zhou by Xuanjing. The title is sometimes translated into English as the arithmetical classic of the gnomon and the circular paths of heaven. This translation gives a sense of the text's scope and character. A gnomon is the upright part of a sundial, the piece that casts a shadow, and the measurement of shadows was central to ancient Chinese astronomy and timekeeping. The text deals with problems related to astronomical observation, calendar calculation, and the mathematical relationships needed to make sense of the heavens. It is not a pure geometry textbook. It is a practical scientific document, grounded in the real problems of measuring the sky and understanding time. And within that practical context, it contains a clear statement and demonstration of the right triangle relationship. The structure of the text is worth noting. It is written as a dialogue between a duke named Zhou Gong and a mathematician named Shang Gao. In this dialogue, the mathematical content is explained and discussed, with Shang Gao responding to the duke's questions by laying out geometric principles and their applications. This format, a dialogue between a ruler or student and a knowledgeable teacher, was a common way of organizing educational and philosophical texts in many ancient traditions. But the content itself is what matters here. The dialogue includes a clear articulation of the right triangle relationship, that in a right-angled triangle, the square of the longest side equals the sum of the squares of the other two sides. It states this as a known principle, not as a discovery being made for the first time within the text, which itself raises a question. If it is being stated as known, then how long had it been known before this dialogue was written? The dating of the Zhou by Xuanjing is contested among scholars, and the disagreement is significant. The text as it survives in its written form is generally placed by historians somewhere around the 1st century BCE, though some estimates push that date back somewhat further. But the mathematical content of the text, the actual geometric knowledge it contains, may be considerably older than the written version that has come down to us. This is a common situation with ancient texts. Writing systems develop. Knowledge that existed in oral or diagrammatic form gets recorded later, often long after the knowledge itself was first developed. Some researchers who have studied the Zhou by Xuanjing argue that the mathematical content it records belongs to a tradition that stretches back to around 1000 BCE or possibly earlier. Others are more cautious and prefer to treat the written date as the operative one. The disagreement has not been resolved, but this is where it becomes unclear, because even if the more conservative position is adopted, Even if the Zhou by Xuanjing is treated as reflecting knowledge from around the 1st century BCE rather than 1,000 years earlier, the Chinese case still presents a significant complication. By the 1st century BCE, the mathematical knowledge in the text was being recorded as established knowledge, not as a new discovery. Someone in China, working in a mathematical tradition that had developed largely in isolation from Greece, had arrived at the same fundamental geometric principle that carries Pythagoras' name, and the way that knowledge is presented in the text suggests it was already part of an established intellectual tradition, not a recent innovation. What makes this particular case especially interesting, and especially relevant to the broader debate about what distinguished the Greek contribution from earlier knowledge, is the visual element within the text. The Zhou by Xuanjing includes a diagram. It is sometimes referred to by the name Suan Thursday, which translates roughly as the hypotenuse diagram. This figure is a geometric illustration that appears to demonstrate the right triangle relationship visually, not just through numbers, not just through verbal description, but through a spatial arrangement that allows the viewer to see why the relationship holds. The diagram uses colored or differentiated areas to show that the square on the hypotenuse can be decomposed and rearranged to equal the sum of the squares on the other two sides. At first, it seems like a small detail, a diagram in an ancient text, but there is a problem with treating it that way. One of the central arguments used by historians who want to preserve Pythagoras' unique status in the history of this theorem is the argument about geometric proof. The claim is that while other civilizations, Babylon, India, Egypt, may have known about the right triangle relationship numerically or practically, it was the Greek tradition that provided a geometric proof, a demonstration that goes beyond specific examples and shows, through visual and logical reasoning, why the relationship must be universally true. This argument has been used to create a meaningful distinction between the Greek contribution and what came before, and it is not an unreasonable argument in principle. But the Suan Thursday diagram in the Zhou by Xuanjing complicates that distinction in a direct way. If the Chinese text contains a geometric demonstration, a visual proof, of the right triangle relationship, then the claim that geometric proof was uniquely or primarily a Greek contribution becomes much harder to maintain. The diagram may not be a formal deductive proof in the style of Euclid, with explicit axioms and step-by-step logical reasoning, but neither is a visual rearrangement argument entirely different from the kind of geometric reasoning that appears in early Greek mathematical demonstrations. The line between a geometric illustration and a geometric proof is real, but it is not always sharp, and when that line is examined carefully, the Chinese diagram sits closer to the proof end of the spectrum than the argument for Greek uniqueness would prefer. This is where the explanation becomes difficult, because China was not, in any well-documented sense, in intellectual contact with ancient Greece during the period when these mathematical traditions were developing. The geographic distance is enormous. The cultural distance is equally vast. The idea that the geometric content of the Zhou by Xuanjing was transmitted from Greece to China, or from China to Greece, during the relevant period is not supported by historical evidence. There is no documented pathway, no known intermediary, no surviving record of exchange that would make direct transmission plausible, and this pushes the investigation back toward the only other available explanation: independent discovery. The concept of independent discovery, the idea that the same mathematical relationship was worked out separately, without any shared source, by multiple civilizations, is not inherently implausible. Mathematics deals with relationships that are true regardless of who discovers them. A right triangle behaves the same way in China as it does in Greece or Babylon. Any civilization that builds structures, measures land, or observes the movements of celestial bodies will eventually encounter the geometry of right angles. And a civilization with a sophisticated mathematical culture, the kind that produces organized astronomical calculations and written mathematical texts, has the tools and the motivation to work out the underlying principles. Some researchers find this explanation fully adequate. They argue that independent discovery of the right triangle relationship by multiple ancient civilizations is exactly what the evidence shows, and that there is no mystery here requiring further explanation. The theorem describes something real and universal. Multiple cultures found it, because it was there to be found. This is a coherent position, but it does not fully make sense as a complete explanation when the specific details are examined more carefully, because it is not just the basic 3-4-5 relationship that appears across cultures. It is the general principle, stated clearly and demonstrated geometrically, in multiple places, across a wide range of time periods. The convergence is precise enough to raise questions that independent discovery alone does not easily answer. And there is a deeper version of this question that the Chinese evidence forces into focus. If Babylon had the theorem numerically, and India had it stated as a geometric rule, and China had it with what appears to be a visual demonstration, all independently, all in sophisticated mathematical traditions, all at times that either predate or overlap with ancient Greece, then what exactly does the standard account of Pythagoras claim to explain? The name persists. The credit remains. But the historical foundation beneath that credit is increasingly difficult to see as solid ground. How many times can the same non-obvious mathematical principle be independently discovered before the explanation of coincidence begins to feel insufficient? That question does not have a mathematical answer. It is a question about how historians evaluate evidence and how much weight is given to patterns that repeat across cultures and time periods. Some believe the pattern reflects something about the universality of mathematical truth and the inevitability of discovery by sufficiently advanced cultures. Others believe the pattern suggests something about the ancient world, about the connectivity and shared intellectual heritage of civilizations that modern histories have tended to treat as separate. Both positions remain alive in the scholarly conversation. Neither has closed the question, and the Chinese evidence, more than any case examined before it, is what makes that question genuinely difficult to set aside. There is a point in any careful investigation when individual pieces of evidence stop being isolated curiosities and start forming something larger. That point has been reached. Babylon, Egypt, India, China, for civilizations separated from each other by vast distances of geography and, in some cases, by centuries of time, have all left traces of the same mathematical knowledge. The traces take different forms. In Babylon, it is a clay tablet with organized numerical tables. In Egypt, it is the implied geometry of enormous construction projects combined with the practices of rope-using surveyors. In India, it is a body of religious and geometric texts that articulate the right triangle relationship as a stated principle. In China, it is a mathematical classic that contains a dialogue explaining the theorem and a diagram that appears to demonstrate it visually. Different forms, different contexts, different languages, different intellectual traditions, but the same underlying mathematical relationship, appearing again and again across the ancient world. When a pattern like this becomes visible, the natural response is to ask what it means. Patterns in history do not appear randomly. They point toward something, toward a shared cause, toward a common source, toward a set of conditions that produced similar results in multiple places, or toward connections between civilizations that have not been fully mapped. But identifying a pattern is only the first step. Understanding what the pattern means is considerably harder. And in this particular case, the explanation is not clear. Different researchers look at the same evidence and reach different conclusions. The disagreement is genuine, and it has not been resolved. The first explanation that is commonly offered is the one that emphasizes independent discovery. The argument goes like this: the right triangle relationship is a feature of physical reality. It is not a human invention. It is a mathematical truth that exists regardless of whether anyone has discovered it. And because it exists in the real world, because right angles appear in buildings, in land measurement, in the geometry of celestial observation, any civilization that engages seriously with construction, agriculture, or astronomy will eventually encounter it. The more sophisticated the civilization's mathematical culture, the more likely it becomes that someone will notice the pattern, work with it, and eventually articulate it in some form. Under this view, the fact that Babylon, Egypt, India, and China all show evidence of this knowledge is not mysterious. It is expected. These were all sophisticated civilizations. Of course they found it. This argument is coherent and should not be dismissed. Independent discovery is a real phenomenon in the history of science and mathematics. Multiple cultures have, at different times and without any shared contact, developed similar tools, similar techniques, and similar ideas in response to similar practical needs. The wheel appears in multiple places. The practice of fermenting grain to make alcohol appears on several continents. The observation that the sun follows a regular annual cycle was made independently by many ancient peoples. Independent discovery does not require communication or shared sources. It requires similar problems and sufficient intellectual sophistication to work toward solutions, and the right triangle relationship, being grounded in the physical world that everyone inhabits, is exactly the kind of thing that multiple cultures might independently discover. But this is where it becomes unclear, because the argument for independent discovery works more easily for simple observations than for sophisticated mathematical knowledge. Noticing that certain triangles have a special property, that some particular combination of measurements always produces a right angle, is one level of understanding. Developing a systematic method for generating multiple instances of that relationship, including instances involving large and complex numbers far beyond any practical construction need, is something quite different. And that second, deeper level of understanding is what the Babylonian evidence suggests. The Pythagorean triples listed on Plimpton 322 are not all simple. Some of them involve numbers in the hundreds. These are not figures you stumble across while measuring a field or cutting a block of stone. To find them, someone had to search for them deliberately. And deliberate mathematical search of that kind implies a level of abstract engagement with the relationship, an interest in understanding it for its own sake, that goes beyond practical application. This raises a question that the independent discovery argument does not fully answer. What kind of mathematical culture produces a systematic search for large Pythagorean triples? Not a culture that merely uses the relationship for convenient construction. A culture that finds the relationship interesting enough to explore beyond the limits of immediate practical need. And if that kind of mathematical curiosity existed in Babylon as early as 1800 BCE, the question of whether it remained entirely isolated from the rest of the ancient world becomes harder to answer confidently. Mathematical curiosity and the knowledge it produces have a tendency to travel. Not always quickly, not always completely, but over centuries and through the channels that connect civilizations, ideas move. At first, it seems reasonable to treat the ancient world as a collection of largely separate civilizations, each developing in relative isolation. That image is familiar and comfortable, but there is a problem with it. The ancient world was more connected than this image suggests. Trade was not a minor or occasional feature of ancient life. It was a central and sustained activity that linked regions across enormous distances. The Near East, in particular, was a crossroads. Babylon sat at the intersection of routes that connected Persia, Anatolia, Egypt, and the broader Mediterranean world. Merchants moved goods, grain, metals, textiles, spices along these routes. And wherever merchants moved goods, ideas moved with them. Mathematical techniques, astronomical knowledge, and practical geometric methods were the kinds of knowledge that had direct practical value for traders, builders, and administrators. They were exactly the kind of knowledge that would travel. And merchants were not the only carriers. Diplomats traveled between courts. Craftsmen moved to where their skills were needed. Scholars were sometimes exchanged between rulers as a form of cultural prestige. In some periods and regions, captured populations were relocated, bringing their knowledge with them. The ancient world was not a world of hermetically sealed cultures that never shared ideas. It was a world in which knowledge circulated, unevenly and imperfectly, but circulation happened. Some researchers believe that mathematical knowledge, including knowledge related to right triangle relationships, was part of what circulated. They argue that a broader ancient mathematical culture existed, one that has not been fully reconstructed from surviving records, but whose existence is implied by the pattern of similar knowledge appearing across multiple civilizations. This is where the explanation becomes difficult, because the transmission hypothesis, the idea that this mathematical knowledge spread through some network of ancient exchange, runs into a serious problem when China is brought into the picture. The connections between China and the ancient Near East during the period in question were not well established. The Silk Road, which would eventually create a more sustained connection, did not exist in its recognizable form until centuries after the mathematical knowledge in the Zhou by Xuanjing appears to have been developed. For the transmission hypothesis to account for China, it would need to propose either a much earlier and less documented form of contact, or a very slow and indirect pathway through which mathematical knowledge made its way across the full breadth of Asia. Neither of those pathways can be confirmed. The evidence for direct transmission between China and Babylon or Greece during the relevant periods is simply not there. So the investigation arrives at a genuine impasse. On one side, the independent discovery argument struggles to account for the sophistication of the Babylonian numerical knowledge and the specific character of what appears in different traditions. Not just a practical observation, but a systematic and sometimes geometric understanding. On the other side, the transmission argument struggles to account for China, where the geographic and historical barriers to direct contact are real and significant. Neither explanation covers all of the evidence cleanly, and this is not a case where one side is clearly right and the other clearly wrong. Both positions are defended by serious researchers. The debate continues because the evidence genuinely supports more than one interpretation. What the pattern itself tells us, regardless of which explanation is ultimately more persuasive, is that the right triangle relationship was not a rare or difficult insight accessible only to exceptional civilizations. It was something that multiple advanced cultures, working across a wide range of periods and places, arrived at and worked with in sophisticated ways. This alone changes the context in which the story of Pythagoras needs to be understood. The theorem does not emerge from a unique moment of Greek genius into a mathematical world that had previously been unaware of it. It emerges into a world where the relationship it describes was already known, in various forms, to a significant portion of the most mathematically sophisticated cultures that had existed up to that point. Some researchers find this conclusion uncomfortable because it seems to diminish one of the most celebrated figures in the history of mathematics. But that reaction rests on a misunderstanding of what the evidence is actually saying. The pattern does not prove that Pythagoras learned the theorem from someone else and falsely claimed credit. It does not prove that the Greek contribution was worthless or entirely derivative. What it does is raise a more nuanced and more interesting set of questions. What was the relationship between the mathematical knowledge already present in the ancient world and the formal tradition that developed in Greece? How much of what Greek mathematicians contributed was synthesis, formalization, or proof of things that were already known in other forms? And is the way credit has been assigned in this case, and perhaps in other cases, fully accurate? These questions do not have simple answers, but they are worth asking, because how a civilization understands the origins of its intellectual achievements shapes how it understands itself. And the picture of those origins, in this particular case, is considerably more complicated than the name of the theorem suggests. The pattern is visible. Babylon, Egypt, India, China, each carrying versions of the same mathematical knowledge. What that pattern means, whether it reflects independent convergence, ancient transmission, or something else entirely, is a question that historians have not resolved, and it is a question that the evidence, taken as a whole, makes very difficult to avoid. There's one more dimension to this that deserves attention before moving forward. The civilizations examined so far are not the only ones that could be brought into this discussion. Other ancient cultures in other parts of the world show signs of geometric sophistication that historians are still working to fully understand. The pattern may be even broader than the cases examined so far suggest. And if that is true, if the right triangle relationship was known and used across an even wider range of ancient civilizations than Babylon, Egypt, India, and China, then the question of how all of that knowledge fits together becomes larger and more difficult still. The explanation that works for 4 civilizations may struggle even more with 5, or 6, or more, and the pattern, already striking, becomes harder and harder to explain away. The evidence gathered so far has focused on mathematics, on tablets, texts, diagrams, and construction techniques, on numbers and geometric relationships, and the question of which civilization understood what, and when. But at a certain point, the investigation moves beyond the mathematics itself and touches something broader, something that has implications not just for how the Pythagorean theorem is understood, but for how the entire history of ancient knowledge is understood. because the pattern that has emerged, the same mathematical relationship appearing across Babylon, Egypt, India, and China, all before or alongside ancient Greece, is not just a mathematical puzzle. It is a question about how history assigns credit. And that question, once it is properly examined, turns out to be more complicated and more consequential than it might initially appear. When a theorem, a discovery, or an invention is named after a specific person, that naming carries an implicit claim. It says, this person was the one who figured this out. Before them, it was not known. After them, it was. The name functions as a marker of origin. And for most of history, this kind of naming has been accepted without much scrutiny. Pythagoras' theorem, Newton's laws, Euclid's geometry. These names feel natural because they have been repeated so many times that they have become part of the basic structure of how educated people understand the history of knowledge. Questioning them feels almost strange, but the evidence examined in this investigation makes the questioning unavoidable. Because if the right triangle relationship was known in Babylon more than 1,000 years before Pythagoras, and stated geometrically in India around the same time he was alive, and demonstrated visually in China, then the naming of the theorem after Pythagoras is, at minimum, an incomplete representation of the actual history. This is where a deeper issue comes into focus. The naming of discoveries after individuals is not a neutral or purely objective process. It is shaped by which civilizations produced written records, which records survived, which languages those records were written in, and which intellectual traditions were most accessible to the scholars who later wrote the histories that everyone reads. These are historical and cultural factors, not purely mathematical ones, and they have had a very significant effect on whose contributions get remembered and whose get overlooked or minimized. Pythagoras lived in the ancient Greek world, and the ancient Greek world had a particular advantage when it came to the long-term preservation and transmission of knowledge. Greek became the dominant intellectual language of the Eastern Mediterranean for centuries, first through the conquests of Alexander the Great, and then through the influence of the Roman Empire and later the Byzantine tradition. Greek texts were copied, studied, translated into Latin, and eventually transmitted into medieval European scholarship. The intellectual inheritance of ancient Greece was continuously maintained through a chain of copying and study that stretched from antiquity into the modern period. This does not mean Greek knowledge was more valuable. It means Greek knowledge was more accessible to European scholars in particular. For a very long time, the mathematical traditions of Babylon, India, and China did not have the same advantage of continuous accessibility to European scholarship. Babylonian clay tablets sat buried under the soil of Mesopotamia for thousands of years. They were not excavated, deciphered, and analyzed in significant numbers until the 19th and 20th centuries. The mathematical content of those tablets, including Plimpton 322, and everything it implies about Babylonian knowledge of right triangle relationships, was essentially invisible to Western mathematical historians until modern archaeology and philology made it available. Before that point, it was not that historians looked at Babylonian mathematics and decided it was less important than Greek mathematics. It was that they could not look at it at all, because the records were not available to them. The situation with Indian and Chinese mathematical traditions was different in detail, but similar in effect. Sanskrit mathematical texts, like the Sulba Sutras, were known to exist, but their content was not systematically studied by Western scholars until relatively recently in historical terms. Chinese mathematical classics, like the Zhou by Xuan Jing, were even less accessible to European historians for most of the period when the standard histories of mathematics were being written. The histories that became canonical, the ones that placed Greece at the center of the story of mathematical development, were written at a time when the full range of evidence was simply not available. And those canonical histories, once established, proved very difficult to revise even as new evidence came to light. But this is where it becomes unclear, because recognizing this historical imbalance does not automatically answer the question of what should replace the standard account. It is easy to say that the history of mathematics needs to be told more inclusively, with proper recognition of Babylonian, Indian, Chinese, and Egyptian contributions. That is a reasonable and widely accepted position among historians of mathematics today. But the harder question is more specific. What exactly was the Greek contribution, if the underlying mathematical knowledge was already present in other traditions? And here the answers are less settled. Some historians argue that what Greece contributed, and what genuinely distinguishes the Greek mathematical tradition from its predecessors and contemporaries, was the concept of formal deductive proof. Not just the observation that a relationship holds, not just a table of examples or a practical method that works, but a logical demonstration, built from first principles, that a relationship must be true, universally and necessarily, in any possible case. This kind of proof is different from a table of Pythagorean triples. It is different from a stated geometric rule. It is different from a visual diagram. It is a form of reasoning that asks not just whether something works, but why it must work, and that answers that question through a chain of logic that can be examined, verified, and challenged by anyone who understands the starting principles. The development of this kind of mathematical reasoning, the historians argue, was a genuine and transformative contribution. It was not something that Babylon, India, or China had in the same form during the relevant periods. Others push back on this argument, and their pushback is worth taking seriously. They point out that the claim that formal deductive proof was uniquely Greek is itself based partly on the limited availability of non-Greek records. If Indian or Babylonian mathematical traditions contained forms of reasoning that approach proof, and some researchers argue that elements of the Sulba Sutras do approach a kind of geometric demonstration, then the distinction between Greek proof and non-Greek practical knowledge may be less sharp than it has traditionally been drawn. The argument depends on what counts as proof, and that turns out to be a question with no single agreed answer. At first, it seems obvious that a formal proof is a specific and identifiable thing. But there is a problem. The line between a clear and general demonstration of why something works and a formal deductive proof in the Euclidean sense is not always easy to draw, and how that line is drawn has a significant effect on how the Greek contribution is assessed relative to the others. There is another dimension to this that the investigation cannot ignore. Ancient Greek writers themselves, the very sources from which the standard account of Greek mathematical achievement is drawn, did not always present Greek knowledge as entirely original. Herodotus, one of the earliest and most widely read Greek historians, wrote about Greek thinkers traveling to Egypt to learn. He described Egyptian priests as the sources of certain kinds of knowledge that Greeks later developed further. Diogenes Laertius, writing about the lives of Greek philosophers, recorded traditions of travel and learning from foreign sources for multiple thinkers, including Pythagoras. These acknowledgments of intellectual debt are present in the ancient Greek record itself. They were not hidden or suppressed. They were simply not given much weight in the histories that later scholars constructed, because the emphasis was on celebrating the Greek contribution rather than tracing its sources. This raises a broader question that goes well beyond the Pythagorean theorem. If Greek mathematical and philosophical achievement was partly built on knowledge acquired through travel and contact with older civilizations, if Egypt, Babylon, and Persia were intellectual sources that fed into what later became the celebrated tradition of Greek thought, then the standard narrative of Greek originality needs to be understood differently, not dismissed, not replaced with a claim that Greece contributed nothing, but understood as part of a longer and more complex story of intellectual inheritance, synthesis, and development that spans multiple civilizations and many centuries. Greece was not the starting point. It may have been, in certain respects, a remarkable synthesizer and formalizer of knowledge that came from many sources. And this is where the explanation becomes difficult, because the question of synthesis versus origination is not only about Pythagoras. It is about how the history of human knowledge is told more generally. If the mathematical traditions of Babylon, India, and China have been systematically underrepresented in the standard histories, not out of deliberate dishonesty, but because of the accidents of which records survived and which were accessible to which scholars, then the distortion is not limited to one theorem and one name. It potentially extends across a wide range of mathematical and scientific knowledge that has been attributed to Greek or later European sources, when the actual origins were more distributed, more ancient, and more global. Some researchers who study this problem argue that the history of mathematics needs to be substantially rewritten to reflect what the evidence, now more fully available, actually shows. They want to see Babylonian, Indian, Chinese, and other non-Western mathematical traditions given proper credit as genuine sources of the mathematical knowledge that the world now uses. Others are more cautious. They acknowledge the incompleteness of the standard account, but worry about overcorrecting, about replacing one oversimplification with another by understating the genuine distinctiveness of the Greek formal proof tradition. It doesn't fully make sense to frame this as a binary choice between honoring Greek achievement and honoring the contributions of other ancient civilizations. The evidence suggests that the actual history is more layered than either position on its own can capture. Knowledge developed in multiple places. It was transmitted, sometimes in ways we can document, and sometimes in ways we cannot. It was synthesized and formalized by different traditions in different ways. And the system of naming that attached one person's name to a universal mathematical truth was a product of specific historical circumstances, not a neutral record of who deserved the credit. What other knowledge sits in this same situation? What other theorems, what other discoveries, what other intellectual achievements carry names that reflect the accidents of historical preservation rather than the full reality of where the ideas came from? These are questions that historians of science and mathematics are actively working on. The answers are not yet fully in, and the process of finding them requires not just looking more carefully at the evidence, but being willing to question frameworks of understanding that have been in place for a very long time. The investigation has moved through a significant amount of evidence by this point. Babylonian tablets with their columns of numbers, Egyptian construction techniques and their relationship to right triangle geometry, Indian geometric texts that state the relationship in explicit terms, Chinese mathematical classics with their visual demonstrations. And through all of that evidence, a pattern has emerged that is difficult to ignore. The same mathematical relationship appearing across multiple ancient civilizations, across multiple centuries, in forms that suggest genuine understanding, not just accidental or superficial familiarity. And yet the theorem carries one name, the theorem of Pythagoras. So what do researchers who have studied this question most carefully actually believe? Because it turns out they do not agree. And the disagreements between them are not minor or technical. They run in several different directions, and each direction raises its own set of questions that are not easy to resolve. The first and perhaps most straightforward view is the one that defends the traditional account, at least in part. Under this interpretation, the historical record is not entirely wrong. It simply needs to be understood more carefully. The argument goes like this. Knowing that a specific set of numbers, 3, 4, and 5, or 5, 12, and 13, forms a right triangle is one thing. Having a table of such numbers, or using such relationships in construction, is a form of practical knowledge. It is useful. It works. But it is not the same as understanding why such relationships exist universally, across all possible right triangles, in all possible sizes and proportions. And it is certainly not the same as proving that this must be true, not just in the cases you have checked, but in every conceivable case that could ever arise. This is what some historians argue Greece contributed, not the observation, not the practical technique, but the formal deductive proof, the logical demonstration that shows why the theorem holds universally, built from first principles, step by step, in a way that can be examined and verified by anyone who follows the reasoning. That, under this view, is what makes the Greek contribution genuinely different. This argument has a certain logical appeal. There is a real distinction between knowing that something works and understanding why it must work. A builder can know that a 3-4-5 triangle produces a right angle without understanding anything about the deeper geometric relationship that makes this true. A scribe can copy a table of Pythagorean triples without understanding the algebraic structure that generates them. These are different kinds of knowledge, and it is not unreasonable to argue that the formal proof, the demonstration of the universal truth, represents a distinct and significant intellectual achievement. This is where the traditional defense of the Greek contribution rests. And for a long time, this was enough to settle the matter for most historians. But this is where the argument becomes harder to maintain than it initially appears, because there's a fundamental problem with the claim that Greece provided the formal proof. We do not have Pythagoras' proof. We do not have a text, a tablet, a papyrus, or any surviving document in which Pythagoras, or any member of his school, lays out the logical demonstration of the theorem that now carries his name. What we have are later accounts, written centuries after Pythagoras lived, that attribute the discovery or the proof to him. We have references, traditions, and attributions. We do not have the original work, and this means that the claim rests, at least in significant part, on inference and assumption, rather than direct documentary evidence. The proof may have existed. Pythagoras or his followers may have produced it, but the certainty with which the theorem has been attributed to him for so long goes beyond what the surviving evidence can strictly support. This raises an uncomfortable question. If the attribution is based partly on inference, is the claim that Greece provided formal proof while other civilizations only had practical knowledge, is that claim itself partly an assumption? Some historians argue that it is, and their argument goes further. They point out that the distinction between formal deductive proof and other forms of mathematical reasoning is not always as clear or as sharp as it is sometimes presented. When the Sulba Sutras state a geometric relationship in general terms and provide constructions that demonstrate it, is that not a form of reasoning? When a Chinese text provides a visual demonstration that the areas of squares on the sides of a right triangle add up in a specific way, is that not a form of showing why? Not just that. The answer depends entirely on what definition of proof is being used. And that turns out to be a question on which there is no single universally accepted answer. If the definition of proof is drawn strictly around Euclidean formal deduction, axioms, logical steps, explicit conclusions, then the claim that it was uniquely Greek may be more defensible. But if the definition is drawn more broadly around any rigorous demonstration of why a relationship holds, then the boundary becomes much harder to maintain. And how that boundary is drawn has very large consequences for how the history of mathematics is told. This is where a third view enters the picture, and it focuses not on the question of proof, but on the question of transmission. Some researchers who have studied this problem believe that the appearance of the same mathematical knowledge in multiple ancient civilizations does not necessarily reflect independent discovery. They argue that the ancient world was more connected than it is sometimes assumed, that knowledge traveled through Persia, through trade networks, through the movement of merchants and scholars and diplomats and teachers, through the kinds of cultural contact that do not always leave clear documentary records, but that can sometimes be inferred from the patterns of what appears where and when. Under this view, what looks on the surface like parallel independent development may actually be a slow diffusion of shared knowledge across regions and across time, a gradual spreading of mathematical understanding through networks of contact that we have not yet fully mapped, and may never fully map with the evidence available. This transmission hypothesis raises its own set of problems. It is very difficult to prove. The absence of documented trade in mathematical ideas does not mean the trade did not happen, but the presence of similar mathematical knowledge in two places does not prove it was transmitted from one to the other rather than developed independently. Both things can look similar in the surviving evidence, and the problem is compounded by the fact that the records we have are fragmentary. Large portions of the written output of ancient civilizations have not survived. What we are working with is a partial record, sometimes very partial, and drawing firm conclusions about patterns of transmission from a partial record is genuinely difficult. This doesn't mean the transmission hypothesis is wrong. It means it cannot currently be confirmed with the same kind of certainty that the evidence for the mathematical knowledge itself provides. But this is where a fourth view comes in, and it is perhaps the most challenging of all the positions in this debate. A smaller number of researchers have argued for something more radical. Their claim is not just that the standard history of mathematics underestimates the contributions of non-Western civilizations, or that knowledge may have been transmitted through routes we have not documented. Their claim is that the picture of ancient mathematical development that is generally accepted, the picture of isolated civilizations slowly and independently building mathematical understanding from primitive beginnings, is itself a modern simplification that does not match the actual complexity of the ancient world. Under this interpretation, there may have been sustained mathematical traditions, connections between intellectual communities, and depths of understanding that we have systematically underestimated, partly because so much of the evidence has been lost and partly because the frameworks used to interpret what survives have been shaped by assumptions that are themselves historically specific. This is a harder position to evaluate because it makes claims about things we cannot directly see. But it raises questions that are worth sitting with. What do we know? What has been lost? And how much of what we think we know is shaped by the limits of the evidence that happens to have survived? None of these four views, the defense of Greek formal proof, the critique of that defense on evidentiary grounds, the transmission hypothesis, or the more radical underestimation argument, is conclusively proven. This needs to be said clearly, because it can be tempting to hear these debates and conclude that one side must be right and the other's wrong. But the reality is more uncertain than that. Each position has genuine evidence and argument in its favor. Each also faces difficulties and gaps that its proponents have not fully resolved. The debate continues among active researchers, and the answers are not settled. At first, this might seem like a failure, like the investigation has not produced a clear result. But it doesn't fully make sense to see it that way. What the investigation has produced is a clearer picture of where the uncertainties actually lie. And that is itself a meaningful result. Consider what is now clearer than it was at the start. It is clear that the mathematical knowledge embedded in the Pythagorean theorem was present in ancient Babylon more than 1,000 years before Pythagoras. That is not a fringe claim. It is supported by actual surviving tablets that have been analyzed by multiple scholars working independently. It is clear that the Sulba Sutras state a version of the theorem in explicit geometric terms, and that the dating of those texts places them in a period that overlaps with or precedes the period of Pythagoras. It is clear that Chinese mathematical texts contain visual demonstrations of the right triangle relationship that do not depend on Greek influence. These are things that the evidence supports. What remains less clear is the question of proof, whether the Greek contribution of formal deductive reasoning represents something genuinely distinct, and how that distinctiveness should be weighed against the evidence of earlier and parallel mathematical knowledge elsewhere. And this unresolved question about proof connects back to a broader and harder question. Some believe the theorem essentially belongs to everyone, that it is a mathematical truth that multiple human civilizations discovered, each in their own way, through their own traditions, and that the attachment of a single name to it is a distortion of something that was actually a shared human achievement. Others insist that the Greek formalization was not just a naming convention, but a genuine intellectual leap, that what Euclid eventually produced in his written proof was qualitatively different from anything that came before, and that this difference matters for how the history of mathematics is understood. These are not just historical positions. They reflect different ways of thinking about what counts as discovery. Does discovery mean being the first to use a relationship, the first to state it explicitly, the first to demonstrate it formally, or the first to integrate it into a coherent system of deductive mathematics? The answer to that question shapes everything else. There's another thread in this debate that is sometimes overlooked. Some researchers argue that even asking the question of who discovered the theorem, framing it as a matter of priority and credit, is itself a way of thinking that may not fit the reality of how ancient mathematical knowledge actually developed. Priority disputes and credit assignment are very modern concerns. The ancient mathematical traditions that produced this knowledge were not, for the most part, engaged in a competition for intellectual credit. They were solving practical problems, building religious structures, training students, developing cosmological frameworks. The mathematics emerged from those contexts, attaching a single name to it, in a way that implies ownership and discovery, may be a framework that was never appropriate to the reality, and may have created a distortion that no amount of historical revision can fully correct, because the framework itself is the problem. What does this leave us with? A mathematical truth that is ancient beyond the reach of any single name, a set of civilizations that understood it in various ways and to various degrees of formality, a tradition of Greek mathematics that built something significant on that foundation, but built it on a foundation that was already there, and a history of naming and credit that reflects the accidents of which records survived, which languages were accessible to which scholars, and which intellectual traditions were most visible to the people who wrote the histories that later became canonical. The scholars who study this question are still working through what all of this means. And the disagreements between them are not a sign that the question is unanswerable. They are a sign that the question is real, and that the evidence demands to be taken seriously. There's a point in any investigation where the evidence has been examined, the arguments have been laid out, and the question that started everything is still sitting there, not fully answered, not cleanly resolved, but understood differently than it was at the beginning. This investigation has reached that point. The theorem of Pythagoras has been looked at from multiple directions. The mathematical traditions of Babylon, Egypt, India, and China have been examined. The historical circumstances that shaped how this theorem came to carry one name have been considered. The debates between researchers who disagree about what the evidence means have been explored. And after all of that, the story that emerges is more complicated, significantly more complicated, than the single name attached to this theorem has ever suggested. That complexity is not a failure of the investigation. It is what the investigation found, and it raises questions that do not have clean answers. Start with what is actually established by the evidence. A Babylonian clay tablet, Plimpton 322, contains columns of numbers that represent Pythagorean triples. Large numbers, sophisticated numbers, numbers that could not have been produced by accident or by simple trial and error. The tablet dates to roughly 1800 BCE, more than 1,000 years before Pythagoras was born. This is not a disputed point among scholars who have studied it. The tablet exists. The numbers are on it. The mathematical relationship those numbers represent is real. The question of exactly what the Babylonian scribes understood about why those numbers work the way they do, whether they had something approaching a general principle or only a practical method, is debated. But the presence of the knowledge, in some form, more than a millennium before Greece, is not seriously questioned. That alone should give pause to anyone who accepts the standard account without reflection. Then there is the Indian evidence. The Sulba Sutras, ancient Sanskrit texts concerned with the geometry of ritual fire altars, contain explicit statements of the right triangle relationship in geometric terms. These texts describe how to construct squares whose areas equal the sum or difference of other squares, and they do so using principles that directly reflect what the Pythagorean theorem says. The dating of these texts is a matter of ongoing scholarly discussion, and estimates vary. Some place them clearly before Pythagoras. Others place them in a period that overlaps with his lifetime. None of the serious estimates place them after a period that would make Greek influence likely. And this raises a question that is genuinely difficult to answer. If the Indian geometric tradition was working with this relationship independently, whether before, alongside, or in a period of possible but unproven contact, then what exactly does it mean to call this theorem Greek? The Chinese evidence adds another layer. The Zhou by Xuan Jing, one of the oldest Chinese mathematical classics, contains what appears to be a visual demonstration of the right triangle relationship, a geometric argument using the areas of squares arranged around a right triangle to show why the relationship holds. The exact dating of this text is uncertain, and scholars differ on how to interpret some of its content. But the demonstration is there, and it is a demonstration that does not depend on any Greek source, and that may represent an independent tradition of understanding the same mathematical truth through a different kind of reasoning. At first, it might seem like these are separate stories from separate civilizations that simply happen to involve the same mathematical fact. But there's a problem with that interpretation. The convergence is too consistent to sit with comfortably. And then there's Egypt. The Egyptian evidence is different in character from the others. It is less direct. There are no surviving Egyptian texts that state the Pythagorean theorem in explicit terms. What there is instead is evidence of construction practices. The use of ropes knotted at intervals that correspond to right triangle ratios, the alignment of massive architectural structures with a precision that suggests applied geometric knowledge, that implies familiarity with right-angle construction in practical terms. Whether this practical knowledge involve an understanding of the general geometric principle is something the surviving evidence does not answer clearly. But the practices are real. The precision of the constructions is real. And the question of what knowledge underlies those practices remains genuinely open. This is where the picture of the ancient world that emerges from this evidence becomes worth sitting with. What is being described is not a collection of isolated civilizations. each slowly and independently reinventing the same mathematical wheel from scratch. What is being described is a pattern spread across Mesopotamia, the Indian subcontinent, East Asia, and North Africa, of mathematical knowledge that includes, in various forms and to various degrees of explicitness, an understanding of the relationship between the sides of a right triangle. The civilizations that held this knowledge were not in regular documented contact with each other in ways that historians have mapped in detail, and yet the knowledge appears across all of them. This raises questions about how knowledge moved in the ancient world that are far from fully answered. But this is where the story of Pythagoras himself becomes important to look at directly, because even the account of what Pythagoras actually did, what he demonstrated, what he proved, what he contributed, is far less clear than the confidence with which his name is attached to this theorem would suggest. Pythagoras himself wrote nothing that has survived. Everything that is known about him comes from sources written centuries after his death, some of them written more than 500 years after he lived. These sources describe him in terms that mix historical and legendary elements in ways that are very difficult to separate. They describe a figure of enormous personal influence, of mystical authority, of mathematical and philosophical insight, but they do not provide a clear and detailed account of a proof of the theorem that bears his name. They attribute the discovery or the proof to him through traditions that had already been passed down through multiple generations before they were written down. This is not nothing, but it is also not the kind of direct documentary evidence that would be required to establish a priority claim in any modern scholarly context. And this is where the explanation becomes difficult, because the mismatch between the strength of the attribution and the actual state of the evidence is not a minor detail. It is central to the entire question. If the attribution rests on late sources, traditions, and inferences, rather than on direct surviving evidence of a proof, then the certainty with which this theorem has been named after Pythagoras is harder to justify than it is usually presented. This does not mean Pythagoras contributed nothing. It means that what exactly he contributed, and how it compared to what existed before or alongside him, is genuinely uncertain, and that uncertainty has consequences for how the entire history of this mathematical truth is understood. Some researchers who have studied this question have come to the position that Pythagoras should be understood not as the discoverer of the theorem that carries his name, but as a synthesizer or formalizer, someone who brought together mathematical knowledge that existed in various forms, integrated it into a broader philosophical and mathematical framework, and contributed something through that integration that was genuinely significant, even if not original in the sense of being first. Under this interpretation, the Greek contribution was real. It just was not what the traditional account says it was. It was not the discovery of a relationship that no one had known before. It was the placement of a known relationship into a new kind of intellectual framework, the framework of formal deductive reasoning and systematic mathematical thought that changed how mathematics was done. This is a significant contribution, but it is a different kind of contribution from origination. Others argue that even this more generous account of the Greek contribution needs to be examined carefully, because the claim that Greece uniquely developed formal deductive proof, while other ancient civilizations only had practical knowledge, is itself partly based on the limited availability of non-Greek records. If Babylonian mathematical reasoning involved something closer to general principles than a simple collection of examples, and some researchers argue it did, then the distinction between Greek proof and Babylonian practice may be less absolute than it has been drawn. The line between a compelling demonstration and a formal proof is not always obvious, and how that line is drawn turns out to matter enormously for how the comparative history is told. A third group of researchers focuses on the question of transmission. They point out that the ancient world had more connections than modern historical accounts often acknowledge. Persia was a point of contact between Greek thinkers and Eastern mathematical traditions. Trade networks moved goods and people across vast distances. Scholars and teachers traveled. Ideas moved through channels that did not always leave clear documentary records. Under this view, some of the apparent convergence of mathematical knowledge across ancient civilizations may not be independent discovery. It may be the residue of contact and exchange that we have not yet been able to map precisely, because the evidence for the transmission is less durable than the evidence for the knowledge itself. This hypothesis is difficult to confirm, but it is also difficult to rule out, and it changes the frame through which the entire story is viewed. What none of these positions provides is a clean resolution, and perhaps this is the most important thing to hold on to. The investigation has not produced a simple answer to the question it started with, the question of who really knew the Pythagorean theorem, and when, and whether the name attached to it reflects historical reality. What it has produced is a much clearer picture of why that question is genuinely difficult. The evidence is real. The gaps in the evidence are also real. The debates between researchers are substantive, not merely academic. And the standard account, the account that has been repeated in textbooks and classrooms for generations, does not survive close contact with the evidence in the form in which it is usually presented. This raises a broader question that goes beyond any single theorem. If the history of this one mathematical relationship is this complicated, if the standard account is this significantly incomplete, then what does that suggest about other parts of the history of ancient knowledge? What other discoveries, what other theorems, what other intellectual achievements carry names and attributions that reflect the accidents of historical preservation and the limits of what earlier historians had access to, rather than the full reality of where the ideas came from? These are questions that historians of science and mathematics are actively working on. The methods are improving. New texts are being analyzed. Old assumptions are being revisited. The picture is getting more detailed, and in many cases, more complex. What the Pythagorean theorem investigation ultimately shows is that the history of human knowledge is not a clean story of isolated geniuses having original ideas in specific places at specific times. It is something more distributed, more interconnected, and more difficult to assign credit for than the naming conventions of modern mathematics suggest. Knowledge developed in multiple places. It moved in ways that are only partially visible to us now. It was shaped by practical needs, by cosmological frameworks, by the requirements of construction and agriculture and ritual, and it was not always recorded in forms that have survived the passage of thousands of years. What we have is a partial record, and reading that partial record carefully, honestly, and with awareness of its limits is the only way to get closer to what actually happened. We are still working out who knew what, and when, and how knowledge moved through the ancient world. That process is ongoing. The story is not finished. And the question, why multiple ancient civilizations appear to have understood this mathematical relationship before or alongside the civilization that gave it a name, remains genuinely open. The evidence points in multiple directions. The explanation keeps shifting. And perhaps that is the most accurate thing that can be said about where the investigation currently stands.